Listening for the faintest whispers from things you can't even see.
Right.
We're talking about the fundamental building blocks, particles smaller than atoms. How do you even begin to study something like that, something that leaves no visual footprint?
Well, that's the core challenge, isn't it, for particle physicists? We can't just put these particles under a microscope.
No.
So instead, we've had to invent these incredibly, ingenious tools, things that can translate their fleeting existence, their interactions, into something we can measure and understand.
And that's really the heart of this deep dive, particle detectors. We've been digging into the sources, explaining how these sophisticated instruments actually work, what the signals they pick up really tell us, and why this tech is, it's not just cool engineering, it's absolutely essential for pushing the boundaries of what we know.
Yeah, our mission here is to get beyond just the names of the big experiments, like CERN or Fermilab, and really look at the principles behind them. How do we build machines that can actually hear the language of particles?
Okay, let's unpack that. It all starts, I guess, with the idea that even though we can't see them directly, particles do interact with the world around them, right?
Exactly. When a particle flies through matter, could be a gas, a liquid, a solid detector material, it leaves a trace.
Like breadcrumbs.
Kind of like breadcrumbs, yeah, or a tiny fingerprint. And a detector's job is basically to be sensitive enough to pick up these almost imperceptible signs.
And use them to figure out everything.
Pretty much. Where the particle went, how much energy it had, its momentum, even what kind of particle it is, its identity.
So the detector is essentially collecting forensic evidence from these particle interactions, and different particles leave different kinds of evidence. They speak different languages, so to speak.
Precisely. Let's start with charged particles, things like electrons or protons. As they zip through material, their electric field, it sort of messes with the atoms they pass nearby.
How does it mess with them? Like just nudges them a bit?
Oh, more than a nudge. They can actually knock electrons completely off atoms. That's called ionization.
Ah, okay.
And that creates positively charged ions and free electrons. Or sometimes they just boost an atomic electron to a higher energy level that's called excitation. But ionization is really key because those free electrons and ions, they're charged.
So you can collect them as an electrical signal.
Exactly. And the amount of energy a charged particle loses this way, it's predictable. It depends on how fast the particle's going, how much charge it carries, and the properties of the material it's passing through. There are even specific formulas, like the Bethe-Bloch formula, that describe this energy loss quite accurately.
Okay, so ionization is a key signature, creating those collectible electron-ion pairs. What else do charged particles do? Is that it?
No, not quite. For light, high-energy charged particles, think fast electrons, or their antimatter cousins, positrons, is another big effect. It's called Bremsstrahlung.
Bremsstrahlung, German, right?
Yeah, it means breaking radiation. This happens when these really speedy light particles get deflected by the strong electric field around an atomic nucleus.
So they swerve.
They swerve, and as they're deflected, they decelerate, and they emit energy in the form of a photon, a particle of light.
So they lose energy by radiating, like a tiny screech of light as they hit the brakes.
Something like that, yeah. A good analogy. And this effect is much, much more significant for lighter particles like electrons than for heavier ones like protons.
Right.
And it gets stronger the higher the particle's energy is, and also the denser the material specifically, the higher its atomic number Z.
Okay. And I remember reading somewhere that their path isn't perfectly straight either, even without these big emissions.
Right, that's multiple scattering. Good point. Even without, major collisions or radiating photons, a charged particle gets countless tiny deflections as it passes near atomic nuclei.
Just tiny nudges.
Tiny random nudges, yeah.
Yep.
They don't cause large turns individually, but cumulatively, they cause the particle's path to deviate a bit from a perfect straight line. It sort of wiggles.
Okay.
And the crucial part here is that the amount of this scattering, how much the path wiggles overall, is inversely proportional to the particle's momentum.
Meaning
A high momentum particle just punches through with very little wiggling, stays on track. But a low momentum particle gets pushed around more easily, its path deviates more. So by measuring that deviation, we can actually estimate the momentum.
That's clever. So for charged particles, we're looking for ionization trails, maybe some braking radiation for the light, fast ones, and this subtle wiggling of their path tells us momentum.
That's a good summary, yes.
But what about particles that don't have a charge? Like photons, the particles of light. They must behave completely differently. No electric field to cause ionization.
They absolutely do. Neutral particles like photons, they don't cause that continuous ionization trail. They tend to interact in sudden, discrete events. Single high-energy encounters, especially at the energies we're interested in.
Okay.
And there are three main ways high-energy photons interact with matter.
The first one people often hear about is the photoelectric effect, right? From like basic physics.
Yes, exactly. That's dominant for lower-energy photons.
Yeah.
What happens is a photon comes in, hits an atom, and it's just completely absorbed. Gone.
Vanishes.
Yep. And all its energy gets transferred to one of the atom's electrons, which is then ejected from the atom.
Huh?
So one photon in, one energized electron out.
Okay, simple enough. Photon disappears, electron gets kicked out. What about Compton scattering?
Right, that tends to happen more with intermediate energy photons. In this case, the photon interacts with an electron, but it doesn't give up all its energy. It's more like a glancing blow, a billiard ball collision.
Ah.
The photon scatters off the electron, transfers some energy to it, and changes its own direction and energy. It comes out as a lower energy photon going a different way. And the electron recoils, taking some energy. Both continue on.
So the photon survives, but is changed, and the electron gets a kick. Got it. And the third one, you mentioned 3. This must be for the really high energy photons.
That's pair production. And this is where things get really, well, Einsteinian. Energy literally turns into matter.
EMC squared territory.
Precisely. If a photon is incredibly energetic, it needs an energy greater than about 1.022 million electron volts, which happens to be exactly twice the mass energy of an electron.
Okay.
And if it passes close to an atomic nucleus, whose electric field sort of facilitates the process, it can spontaneously convert its energy into matter, specifically an electron and its antiparticle, the positron.
Wow. So pure energy becomes a particle-antiparticle pair, just popping into existence near a nucleus. That's mind-bending.
It really is. It shows the deep connection between energy and matter.
So these specific interaction types, ionization, Bremsstrahlung, multiple scattering for charged particles, and then photoelectric effect, Compton scattering, pair production for photons, these are the fundamental processes, the language that detectors are designed to listen for.
Exactly. That's the key. The genius of detector design lies in creating materials and sensors that are highly sensitive to one or more of these specific signatures.
And modern experiments don't just use one type, right? They layer them.
Yes, absolutely. Modern high-energy physics experiments, like those at the LHC, use these huge, complex, layered systems. Each layer uses different detector technologies, and each is optimized for a particular task or particle type.
Like an onion, but for particles.
Or maybe like a complex musical instrument with different sections, strings, percussion, brass, each detecting a different kind of sound, or in our case, a different particle signature.
Okay, this is where it gets really interesting for me. How these different layers are actually built and what they tell us. So let's start right near the collision point, the innermost layers.
Okay, the innermost layer is typically where you'll find the silicon trackers. Their main job is incredibly precise mapping of the paths of charged particles right after they're created.
Silicon, like in computer chips, how do they get such high precision from that?
Well, it is the same basic material, a semiconductor. They're made of thin slices or wafers of very pure silicon. When a charged particle zips through, it ionizes the silicon, creating free electrons and holes places where electrons used to be.
Right, the ionization we talked about.
Exactly. Then you apply an electric field across the silicon wafer. This field pulls the electrons one way and the holes the other way towards tiny metal electrodes patterned on the silicon surface.
And these electrodes are the sensors.
Yes, and they are segmented into incredibly fine patterns, sometimes long, thin microstrips, sometimes tiny squares called pixels, often just micrometers wide.
So like an ultra-high-resolution digital camera sensor, but detecting charge trails instead of light.
That's a very good analogy. A signal on a specific strip or pixel tells you, with fantastic precision, exactly where the particle passed through that layer.
Okay.
Then you stack multiple layers of these silicon detectors, one outside the other. By getting a series of these precise hits in the different layers, you can connect the dots and reconstruct the particle's 3D trajectory.
And if there's a magnetic field.
Ah, yes. Crucial point. These detectors usually sit inside a powerful magnetic field. Charged particles bend in a magnetic field, positive ones one way, negative ones the other. The amount they bend, the curvature of their path, depends on their momentum.
Less momentum, tighter curve.
Exactly. So, by precisely tracking that curved path through the silicon layers, we measure both the particle's momentum, and the sign of its charge.
That makes perfect sense. The magnetic field is the key to weighing the particle and figuring out its charge from the track. And silicon must be good for these inner layers because it's fast and can take a beating.
Yes, very fast response time, which is needed for high collision rates, excellent spatial resolution, as we said, and they're engineered to be radiation hard, meaning they can withstand the intense radiation environment very close to the collision point without degrading too quickly.
Okay, so the tracker gives us path, momentum, charge sign. What's the next layer usually designed for? What happens after the tracker?
That's usually where the calorimeters come in. Their role is completely different. They're not primarily about tracking the path. They're designed to measure the total energy of a particle.
How? By tracking it further?
No, by stopping it completely, by absorbing all its energy.
They just bring the particle to a dead stop.
Right, essentially, yes.
Yeah.
The particle slams into the calorimeter material, and its energy gets deposited within that material. It gets converted into other forms, showers of secondary particles, heat, or often tiny flashes of light that we can detect.
Okay. And you mentioned there are different types.
Two main types, generally. First, there are the electromagnetic calorimeters, or ETALs.
ETALs. What do they target?
They're specifically designed to measure electrons, positrons, and photons.
The ones involved in electromagnetic interactions.
Precisely. ECALs are built from very dense materials, often heavy transparent crystals, like lead tungstate. These scintillate, meaning they produce light when particles pass through. Or they can be sampling calorimeters, made of alternating layers of a dense absorbent material like lead or tungsten, and an active material like a plastic scintillator that generates a signal.
Okay. Dense stuff to make them interact. How does that measure the energy?
Well, when a high-energy electron, positron, or photon enters the dense material of an ECAL, it initiates what's called a particle shower, an electromagnetic shower.
A shower?
Yeah, it's a cascade. For instance, an incoming electron might radiate a photon via bremsstrahlung. That photon, now also in the material, might then undergo pair production, creating an electron-positron pair.
Ah, the processes we discussed earlier.
Exactly.
Yeah.
Those new electrons and positrons then radiate more photons, which create more pairs, and so on. This cascade multiplies rapidly, like a tiny avalanche spreading through the material.
Until
Until the energy of the individual particles in the shower drops below the threshold needed for pair production or significant radiation. The shower eventually dies out. The crucial thing is, the total amount of light produced in the scintillator crystals, or the total charge collected in the active layers, is directly proportional to the total energy of the original particle that started the whole cascade.
Wow. So the ECL basically catches this entire firework display, and the total brightness tells you the energy of the first spark.
Okay, what are the other type of calorimeter?
Those are the hadronon calorimeters, or HCLs. As the name suggests, these are designed for hadrons.
Protons, neutrons, pions, particles made of quarks.
Right. Those particles interact primarily via the strong nuclear force, not just electromagnetically. So when a hadron, like a proton, hits a nucleus in the HCl material, it interacts strongly. It can smash the nucleus apart, creating a whole spray of secondary hadrons and other particles.
Another shower. A hadronic shower. Yes, but a hadronic shower is quite different from an electromagnetic one. It's generally much broader, penetrates deeper, is messier, and involves a wider variety of secondary particles. It develops through strong interactions with nuclei.
Sounds more complex to measure.
It is, because the interactions are more complex, and some energy can be lost in ways that are hard to detect, like breaking up nuclei. So HCLs are typically larger and deeper than ECLs. They're often made of less dense, but still substantial materials like steel, brass, or copper, acting as absorbers, interleaved with active detector layers, scintillators, or gas detectors to sample the energy deposited by the shower particles.
But the principle is the same. More energy in, bigger signal out.
Fundamentally, yes. The total signal collected from all the active layers in the HCl is proportional to the energy of the original hadron that initiated the shower, though the energy resolution is typically not as good as for ECLs.
All right, so trackers for path and momentum, ESCLs for electrons, photons, energy, HCLs for hadron energy. They seem to stop most things. What could possibly get through all that? Is there another layer?
There is. The final outermost layer is usually where you find the muon chambers, and they're there to catch muons.
Muons, they're like heavy electrons, right?
Exactly. They're fundamental particles, leptons, just like electrons, but about 200 times heavier. And that mass makes a huge difference in how they interact.
How so?
Well, because they're heavy, they don't radiate energy via bremsstrahlung nearly as much as electrons do. That process is strongly suppressed for heavier particles. And being leptons, they don't feel the strong nuclear force, so they don't interact strongly with nuclei like hadrons do.
So they don't create big showers in the calorimeters.
Pretty much. They lose energy mainly through ionization, just like any charged particle, but they lose it relatively slowly and predictably. They are very penetrating. They typically sail right through the tracker, the ECL, and the HCL without stopping or showering significantly.
The ghosts of the particle world.
You could say that. So the muon chambers are placed right at the very outside of the entire detector, specifically to identify and track these highly penetrating particles after they've passed through everything else.
Makes sense. How do they work? Are they solid, like the others?
No, they're typically very large volume detectors filled with gas mixtures, often things like argon and carbon dioxide. Embedded within this gas volume is a network of wires held at high voltage.
Gas and wires. How does that detect a muon?
As a muon flies through the gas, it ionizes the gas molecules along its path, just like in the tracker silicon, but now in gas. These freed electrons are then attracted towards the nearest high-voltage wire.
Okay.
As the electrons get very close to the thin wire, the electric field becomes extremely strong. They accelerate rapidly, gain enough energy to ionize more gas molecules, freeing more electrons, which then accelerate and ionize more. It creates a small, localized avalanche of charge right near the wire.
A chain reaction.
A controlled chain reaction, yes. This avalanche produces a detectable electrical pulse on that specific wire.
Huh.
So by seeing which wires in multiple layers of these large chambers register a pulse, we can reconstruct the muon's trajectory outside the calorimeters.
And if you see a track going through the whole detector and hitting the muon chambers, you know it was almost certainly a muon.
That's the idea. It confirms its identity as this penetrating particle.
Incredible. So these massive detectors really are these complex layered systems. Trackers, ECL, HCl, muon chambers, each part specialized, picking up on the unique language or signatures that different particles leave behind through these fundamental interactions we talked about. Ionization, radiation, showers, penetration.
Yes, it's a really beautiful combination of fundamental physics principles and, frankly, incredibly clever engineering. But there's one more absolutely critical piece to this puzzle. Getting those raw signals, the little pulses on the wires, the flashes of light in the crystals, the charge collected on the silicon pixels, turning them into something physically meaningful, like a precise energy in JEV or a momentum that requires calibration.
Ah, right. Turning the raw output into actual usable data. That sounds like it could be incredibly tricky in such a complex machine with millions, maybe billions of individual sensor channels.
Oh, it is. It's absolutely essential. And it's a huge ongoing effort in running these experiments. The raw signal from any given detector element isn't, a direct reading of energy in standard units. It's just a voltage or an amount of charge or a number of digitized counts.
Just a number from the electronics?
Exactly. Calibration is the whole process of figuring out the conversion factors. How much energy does this amount of light correspond to? How much momentum does this track curvature imply? It's needed to turn those raw signals into accurate physical quantities. Think of it like calibrating a very, very complex thermometer or scale, but one with millions of sensors.
How do you even begin to calibrate something like that? Where do you start?
Well, it's a multifaceted process, really. First, you have to characterize the detector's response using known inputs. We often rely on well-understood physical processes as standard candles.
Standard candles, like in astronomy.
Similar idea. For example, we know the mass of the Z boson very, very precisely from earlier experiments. When a Z boson decays, say into 2 electrons, those electrons have predictable energies related to the Z mass. So we look for those Z decays in our data, measure the signals those decay electrons leave in our ecal.
And compare the signal size to the energy you know they should have.
Exactly. By comparing the measured signal to the known energy, we can determine the energy scale for the calorimeter, essentially. Figure out how many signal units correspond to 1 unit of energy, like a JIVI. We do similar things for momentum, using known particle masses and decays in the tracker.
So you use physics you already know well to set the ruler for your measurements in the new detector.
Precisely. Then you also have to correct for non-uniformities. No detector is perfectly uniform, meaning different parts might respond slightly differently. Maybe one crystal in the E-ing HAL is slightly less transparent, or one region of the silicon tracker has slightly different electronic gain. Calibration involves painstakingly mapping out these tiny variations across the entire detector volume and applying correction factors.
So that a particle with a given energy registers the same measured energy no matter where it happens to hit the detector.
That's the goal. making sure the response is consistent everywhere.
Okay.
And finally, it's not a one-time job. You need continuous monitoring and recalibration. Detectors age. Components can slowly degrade under radiation exposure. Temperatures can fluctuate slightly, affecting electronics or gas density. The detector's response can subtly drift over time.
So you have to keep checking.
Constantly. Calibration constants need to be regularly updated throughout the entire data-taking period of the experiment to ensure the data remains accurate and reliable. It's a constant battle against these subtle changes, against drift and degradation.
Wow, that really highlights just how much meticulous work goes into getting meaningful results. It's not just about building the giant machine, but this constant, detailed effort to understand and maintain its performance channel by channel.
Absolutely.
So what does this all mean when we pull it together? This deep understanding of particle interactions, the clever layered detector design, the painstaking continuous calibration. What's the big picture?
It means that pretty much everything we've learned about fundamental particles and forces over, say, the last 50 years, confirming the standard model piece by piece, discovering quarks, discovering the W and Z bosons, finding the top quark, and of course discovering the Higgs boson, all of it relies completely on our ability to build, operate, and understand these incredibly sensitive instruments.
They're how we actually tested the theories.
Exactly. These detectors are how we took our mathematical models, our theories of the subatomic world, and confronted them with reality. They provided the evidence.
They really are our eyes and ears, aren't they? Translating these incredibly brief, tiny signatures left by particles, signatures based on those fundamental interactions into the hard data, the measurements we need to actually understand reality at its deepest level.
Think about the Higgs boson discovery you mentioned. That relied crucially on being able to precisely measure the energy and direction of the particles. The Higgs decayed into often pairs of high-energy photons in the ECK, or pairs of Z bosons which themselves decay.
Using those very calorimeters and trackers we just discussed?
Yes, and the precision needed for that discovery was only possible because of decades of work refining detector technology and calibration techniques. Every confirmed particle property, every measured interaction rate, every search for new, undiscovered particles relies fundamentally on the physics principles and detector technologies we've been talking about.
It's like being detectives, you said. Solving the most intricate mystery imaginable, but the clues are these fleeting energy deposits and tracks left by particles, and our magnifying glass is this multi-thousand-ton, incredibly complex detector.
That's a good way to put it.
These detectors aren't just tools, then. They're really extensions of our senses, allowing us to perceive a whole layer of reality that would otherwise be completely, utterly hidden from us.
And think about the scale of that challenge. You're trying to capture the trace left by something unimaginably small, often traveling near the speed of light, existing maybe for a tiny fraction of a second before decaying.
And then turning that faint trace into fundamental knowledge about how the universe works.
Right. It's an absolutely amazing testament to human ingenuity, persistence, and collaboration.
It really makes you wonder what other whispers might be out there in the subatomic world, or maybe even from cosmology, dark matter, dark energy, signals we just haven't yet figured out the right way to listen for. What other fundamental secrets are just waiting for a new kind of detector, a new technology, a new way of hearing the universe's deepest sounds?
That's the question that keeps physicists building the next generation of experiments, isn't it? Always pushing the boundaries of what we can detect.